In this video, I want to walk through the problem-solving strategy for predicting what these molecules look like using valence bond theory. Now, I have an example I want to walk through while we do this. It's sulfur bonded to 4 fluorines. And I want to use this example because it's one of our expanded octet examples from when we learned about Lewis theory and Vesper theory previously. So looking at this one, I'm going to always still start with the Lewis dot structure because it still gives me the best idea of how things are going to immediately connect. It's still pretty good at predicting that. So my fluorines are in my second row of my periodic table, so they can't expand their octet at all. They have 7 valence electrons, so that means they're going to want 1 bond. Now my sulfurs have 6 valence electrons. However, they are, so that would predict that they would want 2 bonds. Which won't work for this because we won't have enough things to connect. But this one can expand its octet. So while it might want 2, it can also do more than 2. So I'm going to build my Lewis dot structure for this. So I've got my sulfur in the center because it needs the most bonds. It's also the least electronegative. And I am going to put 4 around it. And I should have then 1, 2, 3, 4 electrons from the sulfur being used. It'll have another 2 as a lone pair. All right, I've got a Lewis dot structure. I have an octet around my sulfur. I have 2, 4, 6, 8, 9, 10 around the sulfur. But I've used all 6, if you think about it, of its valence electrons to participate, and I'm left with a lone pair. My fluorine all have 8. So now I'm going to use Vesper theory to predict the electron group geometry around that central atom. And so this has, let me switch colors for this part. This has 5 electron groups. It has 4 atoms bonded, and it has 1 lone pair. So I'm going to go to like all my different geometries that exist for 5 electron groups, and they all are going to arrange themselves around that central atom so that there are 90-degree and 120-degree angles in that trigonal bipyramidal structure. Now, the name of my molecular geometry probably won't be that because I have a lone pair, but when I build this out, I'm going to have sulfur in the center, and I've got my 5 lines. One of these is going to be a lone pair, and the rest will be fluorine. So this ends up being that distorted tetrahedral. Geometry, because we're naming it just based on the atoms that are bonded to it. Okay, so now I have my Vesper theory picture. And I've looked already at my Lewis theory. Now to layer on my valence bond theory. So at this point now, what I'm going to do is try to assign a hybridization scheme. And it's going to need to match the electron group geometry. So I have 1, 2, 3, 4, 5 electron groups that are around this sulfur evenly spaced apart. So what I'm doing here is I'm taking the number of electron groups that are repelling each other. And that's going to tell me the number of hybridized orbitals I need. And I'm not going to count double bonds in that. I'm just counting the things that are going to be repelling each other using Vesper theory. So then I can figure out how many atomic orbitals I'm going to need. And you don't have to do this step. I just kind of like doing it myself. I know I have 1, 2, 3, 4, 5 3d orbitals, and I have 1, 2, 3 3p orbitals, and I have 1 3s orbital. And so thinking about that sulfur atom, the ones that are going to end up hybridizing are going to be I'm going to need 5. So I'm going to take my 3s, my 3Ps, that gets me to 4, and then I'm going to need to grab one of my d orbitals to hybridize them. 1, 2, 3, 4, 5 into sp3d hybridized orbitals. And it's going to leave those d orbitals still open and available. Now, thinking about my sulfur, but those are going to be pretty high up. So they're way up here. 4 left. So then filling in my electrons for my sulfur, remember sulfur has 6 valence electrons. So I'm going to come to my hybridized orbitals and I'll go 1, 2, 3, 4, 5. I'm putting 1 electron in each orbital first before I pair them up, and 6. Okay, so now looking at this, what I see is that I'm going to have a lone pair in my hybridized orbitals, and I'm going to have 4 uh, bonding orbitals that have 1 electron. All right, so now I know my hybridization, which is great, and I can now sketch my atomic orbitals and hybrid orbitals onto the atoms of the molecules, and then draw this picture and then label them as sigma and as pi. Give myself a little bit more room here if I can. All right, so let's build this. I'm going to switch colors. All right, so I'm going to put my sulfur in the middle. Actually, let's keep black. And I know this is going to have these 5 hybridized orbitals that'll be spaced as far apart as they can. So I'm going to have 1 going up and down, and then I'm going to have 3 that are going to come out in the equatorial plane. And I like putting in the wedges and dashes even here just to kind of help me keep track of the overall picture of this. All right, so now in one of these, I have a lone pair. I'm going to put this right here. And so I'm not going to do anything with that orbital. It has 2 electrons in it. It can't overlap and share it with more electrons. There can only be 2 per orbital. The rest all have 1. Now, I have my fluorine that are going to be coming in. And so my fluorine are going to come in, and they have to bond. And so now my fluorine atoms can't hybridize with d orbitals. However, it does have 7 valence electrons. It only has 1 that is alone. And so that would be 1 p orbital, or it would be a hybridized orbital. At this point, when you think about what is that fluorine going to do? Is it going to keep all of its valence electrons and then just have that 1 in a p orbital, since it doesn't have to worry about anything else bonding to it? Or is it going to hybridize it so that way the lone pairs are spaced as far away as possible from the bonding atom? And honestly, like at this point, it's like you'll get the same answer no matter which way you look at it. I think of these fluorines as hybridized. I think is the preferred way, because then those electron lone pairs are going to be able to occupy hybridized orbitals that'll be spaced equally away from the bonding orbitals. And so that fluorine is going to come in as, since it has 2s and 2p, and it's going to have 3 lone pairs and 1 bonding orbital. It's going to have sp3 hybridized orbitals as well. So they're going to come in and they're going to overlap as sigma bonds and bring in an extra electron to each of these. And you can then think of these as having their other hybridized orbitals as well. Kind of drawing them poorly. And these each have 2 electrons in them because they are the lone pairs around our fluorine. And so they'll come in and bond that way. And at that point, then we have everything placed. And so if we want to identify our sigma bonds and our pi bonds, we've got sigma bonds between the sulfur and the fluorine. So I have 4 sigma bonds. And I have no pi bonds because I don't have any 2 p orbitals coming in overlapping. So I have 0 pi bonds for this one. Bonds. All right, next there's a practice problem for this. Give it a try before you watch the next video.